I just heard what she said. The chain rule, 2.6. Come try our wassail. 100% pure Worcestershire sauce. Okay. 2.6, the chain rule. The chain rule. We're recording. Yeah. The chain rule is even more powerful, as I mentioned already, than the power rule. If you think about this little picture here, right, that's a bunch of what? Chains, right? There's a bunch of chains, and they're linked together. Chain's pretty strong. So what you could do is you could think of this chain as actually some parentheses that have expressions in them, and then the links that are the sideways, you could think of those as just being little spot welds, right? Which we could put little dots for spot welds. They're like multiplication symbols. This is essentially what the chain rule is. It's going to link together a bunch of factors, a bunch of expressions that are going to be linked together by multiplication. Okay, that's what the chain rule is. What the chain rule does is it triggers a chain reaction whenever you have a function that is a composite function. That's when we're going to use the chain rule. And what is a composite function? Well, it'd be like f of g of x, right? It's a function inside of another function. So you can think of this as like those Russian nesting dolls, right? You have this big outer doll, and then you open its head, and then inside there's another doll, or maybe they break at the midsection, I don't know. But then you keep opening them up, and sometimes you run out of dolls. I don't know, but you just keep taking them out, and they get smaller and smaller. So every time you unpack it, the next doll is smaller because it has to fit inside. And that's kind of the idea with the chain rule. As we unpack these composite functions, every single link in the chain is going to be one of those nested dolls, but it's going to be a smaller and smaller piece every time. So if you've ever played this game, right, you recognize this game? This is Mousetrap. And it's good to explain the chain rule because the chain rule is kind of like, it's called the chain rule for like chain reactions, also links of chains. So how it works, right, you spin the wheel at A, right, and A causes B to turn, which then, in fact, I don't know, this has a little clicker on it, and it makes the C flip back and forth, which then affects D, which kicks the boot. The boot then knocks the ball off, which travels down F, down this spiral to G. At G, travels down the tray, hits this little bar at H. The little bar wiggles the top where this other ball is waiting at I, which rolls down at J and then falls into the tub, which is decreasing right there. So there's a hole in the tub at K. The ball falls down at K, which hits the trapeze at L where the man is standing backwards, and he does a double backflip into N or single backflip. And he lands into N, and then, of course, N is on a little lever too, so it causes this to ricket down.
Teachers and students, please find this interruption for these announcements. Today is the start of final voting for homecoming king and queen.
And anyway, it captures the mouse.
Voting will run until
Like
Wednesday. Also, NVHS Capital Ball will be Friday, October the
like a
15th.
Rube Goldberg machine, right? That's a little contraption, chain reactions.
Tickets will be on
Tom and Jerry cartoons, you ever see those? Those were always good. Tom was always trying to come up with clever ways to catch Jerry. And of course, Jerry was always clever enough to circumvent him. But here's what this is in the chain rule.
Also during lunches, Worst Bowl t-shirts will be sold. They are $15.
Get your Worst Bowl t-shirt.
$25.
Might be too late for you at home.
And students, if you
Okay.
did not get your report card yesterday,
This is Leibniz notation. This is Leibniz notation. We read this as...
please make sure you bring in notes from a parent or a doctor to cover those absences.
The rate of change of P with respect to A. Okay? So in Leibniz notation, we can write this as dPdA, which is the rate of change of P with respect to A. So that's essentially what happens. We do something at A, and ultimately down the line, it affects P, right? Through a sequence of chain reactions. So this would be kind of the end result. dP dA, the rate of change of P with respect to A, is equal to the rate of change of B with respect to A. That means this is your independent variable in the denominator. So if doing something to A affects B, B then has an effect on C, C then affects D, D affects E, E affects F, F affects G, G affects H, H affects I affects J, J affects K, K affects L, L affects M, M affects N, N affects O, and then O ultimately affects P. And there's the chain reaction. And notice each of those chain reactions, they are spot welded together with the multiplication symbol. And multiplication is important because in Leibniz notation, these things refer to differentials, which we can treat as individual quantities. And notice what happens all the way through. What happens to your dBs? They divide out. Your DCs divide out. DDs, DE, DF, DG, DH, TI, DJ, GK, JK, JM, toy boat, toy boat, toy boat, toy boat, toy boat, whatever. So we got dP, dA. That's what it ends up being. So that's the chain rule in action, an extreme case of the chain rule. Okay, one thing affects the other. So without the chain rule, we can find derivatives of functions like this. In fact, let's do it. What would y prime be? 2x, good. What would y prime be on the second one? Cosine x, good. What would y prime be on the third one? 3. And y prime on this one is? 1 minus secant squared. Okay, so nothing wrong with those. With the chain rule, though, we can find derivatives of these. Let's try them. Y prime is 1/2 x squared minus 1 to the negative 1/2. But does that work? No, because you know why? This is not just, if this were just the square root of x, right, that would be x to the 1/2. Then it would just be 1/2 x to the negative 1/2. But what's different about this one is it's got a function inside of a function. Instead of just plain old x on the inside, it's another function of x, x squared minus 1. So we'll need the chain rule for that. So right now it's, This one's sine of 5x. I guess we don't really need the chain rule. We could use composite identities, right? Call that sine of 4x plus x. And then we can use the composite identities until we get down to sine of single x's. And then we can just use a product rule. But who wants to do that? Not even I do. So this is not just going to equal cosine of x or cosine of 5x because we don't have just plain old x on the inside, do we? We have a function of x, a 5x. So we're going to need the chain rule for that because we have a composite function. So that one's, Same thing here. We don't really need the chain rule. We could expand that out to the 7th power. Who feels like expanding that out? I don't. So if I leave it like that, if it were just x to the 7th, right, I know how to find the derivative of x to the 7th. It's 7x to the 6th. But what about blob to the 7th? I don't know. I think we need a chain rule. I have a composite function. I have a function within a function. Same thing here. That's tangent of the quantity x squared. I know tangent of x is secant squared of x, but how do you deal when it's a function of x that's other than x, but like something like x squared? So all of these are composite functions. They have another function of x inside of them. And that's when the chain rule is useful. It's useful for unpacking these composite functions one layer at a time. The nesting dolls, one layer at a time. All right, so here's the chain rule. If y equals f of u is a differentiable and therefore what function? If it's differentiable, continuous function of u. I use u because we're going to be using something called u substitution later. So get your mind out of the gutter. It's a function of u. And if u is g of x, if u is a function of x, and it's also differentiable, then the derivative of y with respect to x is going to be the derivative of y with respect to its variable u times the derivative of u with respect to its independent variable x. And that's how we would write it. And notice we multiply the results together. And then why does that work? What happens with the du's? They divide out and we're left with dy dx. Now, that's Leibniz notation. We're going to be doing it primarily with function notation. It's a little bit easier to understand. So here's the equivalent version. If we're taking the derivative of f of g of x, Notice g of x is inside your f of x function. You can unpackage the derivative one layer at a time, working from the outside in. That's the important part. So what's the outside function here? F of blob, right? So what's the derivative of f of blob? F prime of the same blob. And then put your little spot weld there for the chain link, right? Times, now you work inside one layer, and what do you see? You see the inside function, which is g of x. So now you're going to multiply by the derivative of g of x, which is g prime of x. Okay? Now you can even go in one more layer. You could say, what's inside the g of x function? X. So if you want, you could then multiply by, what's the derivative of x? 1. And so notice we have a composite function there, we have a single function there, and we have 1. So they get smaller as you unpackage them. So if you were to package it back up, the 1 would go inside here, this would go back inside there, and of course that goes back inside the f, and we have that. Okay? So if you think about the chain rule as unpackaging functions, and you're multiplying by one derivative at a time, and you're just multiplying the results together. It's like peeling an onion, right? Peel one layer at a time. How many of y'all ever peeled an onion? Yeah? Yeah, you peel an onion, you break it apart, right? Yeah, it's easy, right? They're layers. When using the chain rule, it's vitally important to rewrite if necessary so you can clearly identify the layers. I think we have time for this example here. The derivative with respect to x of the square root of blob, right? Let's go ahead and rewrite that as blob to the what power? 1/2. Now I'm going to use different flavors here to show the layers. What's the inside function? X squared minus 1. It's inside the square root function. What's the outside function? The blob to the 1/2. So here we go. We rewrote it. We rewrote it. Now we're ready to differentiate it. We work from the outside in. So what would be the derivative of blob to the 1/2 by the power rule? 1/2 blob to the negative 1/2. And you just rewrite the blob. It's one layer at a time. Pretend like you don't even see the inside part to differentiate it until you finish the outside layer. Times the derivative of the inside layer. What's the derivative of x squared? 2x. So you have two layers. You have two factors. And now if you simplify, your 2 times 1/2 becomes 1. You're left with x over the square root of x squared minus 1. And that's the answer. That's the chain rule. You're peeling an onion. You're unpackaging the nesting dolls. One derivative at a time, working from the outside in. That's it. We'll pick up there tomorrow.